Okay, welcome back to the second lecture of gravitational waves.
Okay, good. So I'm canceling this not because I don't agree with what is written, but because it's by now it's redundant. We all believe that. Okay. So yesterday was a bit of a trailer. No, was a kind of overview of the setup where gravitational wave physics is going to be important. I will spend 20 more minutes about this overview, just giving you some flavors of what are the final results that we're getting, and then starting from the second half of this lecture until the end, then we do the boring stuff, you know, derivations, and we really put our hands into the physics that led us to the nice results. So you remember the first nice result was the derivation of the period. You remember? So you have to find what was the typical period, the typical lifetime, sorry, of a binary. The typical lifetime, let's call it. You remember? So in our problem, what is the physical quantity we have which has dimension of time? So we have a binary, we have the total mass. So the total mass has dimension of time, okay? Nobody should be scandalized anymore. Mass is time because I have g Newton for free. And g Newton times mass is a length, which is the same as time, okay? But this is a time which is very, very short, in microscopic, you know? It's 10 to the minus 6 for solar mass, for instance. So how do we make astronomical time with this? Well, we have V, basically. And the V enters to some large power, which I don't remember right now. That's embarrassing. But, yes. No, this is for the lifetime. Okay, let's rederive it quickly. No? You remember, was E divided by E dot. This, by definition, is this time. So E, you remember, was 1/2 eta mv square, and the E dot was eta square times some factor here in front, v to the 10. And you remember, E dot is dimensionless, E is not. There is a G, of course, and the G adjusts this to be a time, and so we have Gm v to the 8. Okay, you see, it's easy to remember. This is the typical lifetime of a binary. This tells you that if we see some compact object binaries in our galaxy, you remember how many we see them? Sorry, minus, thanks, of course. Otherwise, it would be very short. It would be even shorter than the microscope. Yes, thank you. It's -8. You remember, we see 18-ish, 20-ish binary system made of 2 pulsars, made of 2 neutron stars. Probably there are many more because we only see the pulsar that point to us. But basically, and they are with a velocity of order 10 to the minus 3, 10 to the minus 4. So that means this is 10 to the minus 6 in second. This is 10 to the minus 4 in dimensionless unit because velocity is dimensionless. Then it's easy to make a huge number. So just as a rule of thumb, the typical rate per galaxy, the galactic rate of this event is of the order of 1 event per mega year per galaxy. The typical rate per galaxy is 1 per mega year, 10 per mega year. I mean, I'm not really caring about factor of 10-ish. So that means that if you want to see at least one of these events in the lifetime of your detector, you better look at least how many megaparsec. You remember? So this is a mega year. In some understanding of my handwriting is mega year. Okay, now it looks more like a mega year. Okay, this is the typical rate per galaxy. It could be 10 mega years, but again, let's not be picky about factor of 10 at this level. So, if you know the distance between galaxies of the order of few megaparsec, and the number of galaxies grows with the cube of the distance, of course, because it goes with the volume, what is the typical distance to which you think you can see? You need to go in order to see at least 1 per year. So, with the distance reach of 100 megaparsec, if you can see things to 100 megaparsec, given that the intergalaxy distance on average is few megaparsec, you expect to be able to increase by a factor of 10 to the 6 the number of events. So instead of 1 per mega year, you go to 1 per year, if you can see up to 100 megaparsec. And this is more or less exactly what LIGO has done. Has seen two binary neutron star, 2 and 1 is the same at this level. Has seen 2 binary neutron star, and to a distance to around 100 megaparsec. Of course, it has seen 80 more binary black hole, but binary black hole, they have farther distance reach because they are more massive. Okay, so with a distance reach of 100 megaparsec for binary neutron star, given this rate, you expect to see a few per year. That's exactly what you have seen. Binary neutron star, they are more massive, so you expect to see to farther distance, and since the rate increases the cube of the distance, then it's much more likely to see binary black hole than binary neutron star. Okay, so just to give you the order of magnitude, this is sort of the order of magnitude, 10, 100, up to 100 per mega year per galaxy, 10 per mega year per galaxy, and this is the distance reach for binary neutron star. So let's make a little bit of a math. How do we get to this reach? To get to this reach, we must have a detector which measures NH, which is, you remember, what is the gravitational perturbation? The gravitational perturbation is GM over distance. Okay, this is the Newtonian potential sourced by an object. Okay, and this is the same as the gravitational perturbation. So the gravitational wave is actually a bit smaller than this as an amplitude. We'll derive this, but this is just heuristic. So there is a V square. Yes, the gravitational potential is if you like, is the Schwarzschild solution. No? The Schwarzschild solution, you have the potential is the perturbation from Minkowski. So you can guess that the gravitational wave has a perturbation which is of the same order of magnitude. Actually, what will demonstrate that there is a V square suppression. So the amplitude of the gravitational wave is even smaller than the gravitational potential. But as an order of magnitude, you can expect that when the two objects are very relativistic, and at the end we have seen only objects merging. Okay. So at the end of the day, the typical instantaneous amplitude of the wave is of the order Gm over d, Gm over the distance, which is of the same order of the Newtonian potential. But in general will be smaller, okay, because there is velocity square suppression. Again, this velocity square suppression, you don't get it by heuristic argument because velocity is dimensionless. So by dimension could be velocity to any power, but we'll demonstrate that this is actually V square. We'll demonstrate later today. Okay, so yes. Yes. Source and observer. So we observer on Earth. Actually, observer could be anywhere in our galaxy. It doesn't make much difference, no? The galaxy with respect to something outside the galaxy, and the distance to the galaxy of the source. No. This is okay. For let's say Kumovin distance for the moment, because for short distances, I mean, as long as the redshift is much smaller than 1, like for neutron star, it doesn't make much difference. At the end of, in the last lecture, I will tell you how this is corrected by the cosmological expansion. Basically, by the cosmological expansion, this equation stays correct. It's like this, but what you actually do, you multiply both the numerator and the denominator by 1 plus z. So basically, what you measure is this shifted mass. You don't measure the intrinsic mass of the object. You measure the shifted mass, and you measure the luminosity distance. But this is a bit non-trivial. I will demonstrate probably in the last lecture, but for sure before the end of the talk. But okay, this is just to give you the order of magnitude. So given the rate that we expect, 1 per mega year per galaxy is sort of what we expect from our galaxy again. No, we see 10, 20 binary neutron star. They are 100 omega year to billion years away from coalescence because of the computation I made earlier. So you expect that, I mean, of course we don't see all of them because we need the pulsar to point to us. So we expect to see many more, but not 10 to the 6 more, 10 to the 3, 10 to the 4 more. So at the end you expect 1 per mega year roughly. So 1 per mega year means that you have to go to 100 megaparsec to see 1 per year. So let's see what is the sensitivity that we need to see things at 100 megaparsec. So this is 100 megaparsec. And you know, GM is a length, as I taught you yesterday. GM is a length. For binary neutron star is, let's say, it's 5 kilometers. No? Binary neutron star must have a total mass of 3 solar masses. 1 solar mass converted to length is 1.5 kilometers, so this is the distance. Then we need to convert kilometers to megaparsec. So kilometer to parsec was a 10 to the minus 13. Then this is megaparsecs, there is a further 10 to the 6. So overall, this is 10 to the minus 20-ish. Again, let's not be too picky. So this is the typical sensitivity we need for the detector. So this already sounds crazy, no? Because already it's hard, to measure any gravitational potential for anything inside our galaxy. Imagine, we are on the Earth, we feel the gravitational potential of the Earth, we feel the gravitational potential of the Sun, and that's it. It's very hard to measure the gravitational potential of anything else in our galaxy. And this is of the same order of the gravitational potential, but of something outside our galaxy. So indeed, the distance is 100 of megaparsec, is not kiloparsec. So how on Earth can we ever even think of measuring this 13 order of magnitude smaller than what is any gravitational field produced by any other object in our galaxy, which we don't see either? Well, because this is the amplitude, but here there is a cosinus of the phase, and again, I'm not really very friend with this board. Okay, so what you expect to see is a signal like this. Okay, qualitatively, we kind of demonstrate that this is a kind of shape, and of course, a static signal could be 10 order of magnitude bigger than this, but it's static. This is a typical frequency. So what we're gonna measure is something that is changing with, is not only have a specific frequency, but as a frequency pattern. You see here I designed it qualitatively, but I kept the qualitative features. The frequency is increasing, the amplitude is increasing, and this specific pattern that allow us to detect something which is 10 order of magnitude smaller than gravitational perturbation, which are static or almost static. Because basically what we have qualitatively is, that we have a huge, if we write qualitatively what is h in frequency, so h tilde, so at zero frequency we have some huge noise level, and then the noise hopefully goes to 0, and then at some point you have your signal that has some 10 to the minus 20. Of course, h is dimensionless, so h tilde is dimension of time. So here I may be sloppy about dimension. And so this is the kind of signal that we see. And then, of course, this we have to compare with the noise of the detector. Okay, so we see something that goes like this, that has a specific pattern in frequency that we'll demonstrate. Yes, f to the minus 7/6. And this we have a detector which has a given sensitivity. So in particular, it will be something like this between 1000 hertz and 20 hertz. So we can expect to see things in this narrow window with this specific shape. And so, yes, we can reach this incredible sensitivity, but just in a narrow frequency. So in a narrow frequency beam, we can see things to 10 to the minus 20 in perturbation. But of course, if you go to a higher range, a different range of frequency, forget it. We are swamped by all sorts of noise, but all other sorts or noise or astrophysical effects. This is Earth. Okay, so what we need is, this is just the amplitude. So what we need is really a very, very good description of this, because what we want to do is that, again, qualitatively, we have some huge amount of noise. I mean, this noise looks like monochromatic, but it's not. The noise is superposition of all frequencies. So you have noise like this, you have noise like this, you have noise like this, you see? So you have all components of frequency in your noise. And then, can I change color? Yes, color. And then I have a tiny signal. Okay? I have this. So the idea is that I correlate my pre-computed waveform. Okay, this should be equal to that. Okay, I almost made it equal. Yeah. So I should get my pre-computed waveform, correlate with the output of the detector that will contain the noise and this, and hope that I get the right signal. So the output of the correlation, you see, these two are exactly the same. So the output of the correlation will be, now imagine this is a cosinus, this is a cosinus, the product is a cosinus square. The cosinus square is always positive, and then the piece, when I integrate it over time, then this correlation will do something like this. Whereas the correlation of this random noise with my detector will, okay, let's do the red, sorry. We'll do something like this. The red, the correlation will be something like this. And then ends when the signal ends. And then the correlation with the noise will be something like this. Okay, so this is actually what we see after taking the correlation of a signal. But of course, we have to catch the right signal, because the signal will depend on a lot of astrophysical parameters, on the masses, on the orientation, and so on. So if you don't model the right signal, then the correlation will be sloppy, and then it will pop out of the correlation of the signal with the noise. So in order to do that, we need to model very well this part of the signal. This part of the signal is crucial, no? Because if you get the amplitude wrong even by a factor of 2, when you correlate, yes, you lose a factor of 2. But if you get the phasing of the signal wrong, imagine you are correlating a cosinus of some frequency with a cosinus of a different frequency, then you take the correlation, then you go up and down. And then you are not always positive in this correlation. So let's see what we need. My goodness, what I did. Okay. So let's see what we need for this correlation to have success. We need a good determination of the phasing. Oh, let's go back. We need a good determination of the phase. And the phase, okay, I write something that should surprise you. Now I write it as twice. The phase is the integral of the phase derivative. Okay, that's trivial, no? Omega is the angular velocity. It's phi dot, so I integrate omega over time. I just put a factor of 2 because this is orbital angular velocity, and the phase of the gravitational wave is twice the orbital, because when I have two objects, when they go half away, they go back to the same situation because the observer doesn't know which is which, and so half a period is already one period of the gravitational wave. Half orbital period is one period of the gravitational wave. So there is this factor of 2, but this is not very important now. So now let's look at this. How do we estimate this? How do we estimate this? Well, this is omega. Let's say you remember omega depending on v. We are on circular orbit, so r, omega, v, they are all the same thing. So instead of writing omega, we write v cube dt, and there was a gm, 1, 2 over gm. Of course, this is the inverse of time. The gm is the right dimension. You remember v was gm omega to the 1/3. So, okay, I haven't gained much. I mean, this is basically tautology. Now, this is a mathematical identity. So let's introduce some physics. So here I put dE in dE, dE in dV, and dV. Again, this is a mathematical tautology. I have done nothing. But now the physics is much more interesting. Look at this. This is the flux. I mean, I call it flux, but it's really an E dot. This is E dot to the -1. This is the E in dV. Okay? So look at this. I have traded my knowledge of the phase, which is crucial to take the correlation with a very noisy output of the detector, for a knowledge of the dynamics of the system. I need to know how the energy of the binary system changes with V, because, you know, physically what happens, no? I have my binary system, it's radiating gravitational wave. I'm assuming we are in a regime there's nothing around. We are kilometer size, hundreds of kilometer size. Astrophysically, there is nothing. They are in vacuum. They are objects in vacuum, okay? So you can forget any plasma, fluid, nothing. They're just two-point particles interacting with gravitational field. That's the beauty of the gravitational wave, because it's very simple to model. It's just pure GR. There's no, I mean, astrophysics can be very rich, but at the same time, very bothering, because if you start putting magnetic dynamics, gas, and so on, I mean, you don't get out of it just because it's too complicated. These systems are very simple. They just respond to GR. So you have to know how the energy changes with the change of V, and how much energy they leak. How much energy they leak, and to know the change of V, which is the change of frequency. You remember, V is related to frequency. We are under Kepler's law, so velocity, frequency, radius, they are all the same. I mean, they're all related. So we need to know how much energy is leak, and how much this energy leak reflects into a change of frequency. And that's it. We have these two functions, we know the dynamics, we can compute the phasing. We don't even, I mean, in principle, once you have the Hamiltonian of the system and you know how much is leaking, you just put in a computer, you solve the equation of motion, and from the equation of motion, you compute the waveform in a way that I will show you later today or tomorrow. But this is just a shortcut, okay? I'm giving you the shortcut. And basically, suppose you want to work in any theory of gravity, might not be GR, all you need to compute to see what is the effect of your theory in GR into the dynamics of the phasing, which is what we actually measure because we want to take this correlation, are these two functions. So let's plug in the Newtonian values of these two functions. So we get 2 over Gm. So I have a V cube that was there from the beginning. So I have dE in dV. dE in dV is eta EV. You remember, E, let's call it, is the Newtonian energy. It's minus 1/2 reduced mass. Reduced mass is symmetric mass ratio times mass times V squared. I take a derivative, so it's the, and here I have those, the target coefficient, 32 over C, whatever. I have 1 over G. Sorry, I wrote E, but this is an M. Yes. What's happening? Go away. Go away. No. It doesn't go away. And okay, let's leave it there. You will go away at some point. So here was a coefficient, and there was V to the 10, and there was an eta square. Okay, you remember, this was the formula for the flux, which we haven't demonstrated. I just throw it in. You remember, it was a dimensionless thing. It was eta square. Again, it's non-trivial. We'll demonstrate. It was V to the 10. Highly non-trivial to get the V to the 10. We'll demonstrate. But it cannot be anything else. It can be symmetric mass ratio to some positive power and V to some positive power. That we'll demonstrate. And so look at this, and then at the end, and all of this in dV. So let's make some room here. This will give Gm, and Gm simplifies because this is the phase, one which is dimensionless, expressed as a function of V, which is dimensional. So it should go away any dimension. So there is a 2. We don't care the 2 because there is the C. Let's put the proportional factor here. And so we get integral in dV, V to the 6. But of course, there will be correction. This was just the Newtonian part. So there will be correction to the Newtonian energy. There will be correction to the Newtonian flux. Of course, Newtonian, there's no flux. That's called the leading order of the flux. Again, I call it a flux, but it's an E dot. It's not an energy per time per surface. No, it's an, you should call it luminosity. Sorry, luminosity. It's luminosity. It's energy radiated per unit of time. And so we have all sorts of correction. Okay? And so you see, unless you get these two functions. Yes? Ah, thank you. Ah, sure. I haven't, again, we'll demonstrate, we'll find the first order correction. So what happens is that Newtonian energy is minus 1/2 eta mv squared. Okay? But this is Newton. You know the general relativity has correction to it. Even in the Schwarzschild case, you can compute them. I mean, it's standard textbook exercise. And then you get some corrections. These are just general relativistic correction to this to the Newtonian energy. I mean, you shouldn't be surprised. No, here you get, for instance, for the potential, you get terms like Gm over r square. Gm over r square, I traded as V to the 4. This is V to the 4, and so on. And then you get all sorts of correction in general relativity. We'll compute specifically this kind of correction. For the flux, we'll compute, yes, some sort of correction. For the flux, you get the V to the 10 divided by, sorry, eta square divided by G. Here there is the coefficient, the number which we don't care, and here there is also correction. And you shouldn't be surprised that here the corrections are only in even powers of V's, because this is the energy of circular orbit. So it shouldn't change if V goes to minus V or time goes to minus time. Whereas in the flux, you also get odd power. Not a V to the 1, but V to the cube, V to the 4, V to the 5, you get also. All of these are general relativistic correction. And we'll compute the first one again. But going back, yes, did I answer your question? Who was? Yes. When we go back, then we get to this formula here. Now I don't have any more space. So, but anyway, what you see is that this is dV over V. It gives you 1 over V to the 5. So V is small. I mean, it's smaller than 1 for sure. So 1 over V to the 5 is large. So 1 over V to the 3 is large. 1 over V to the 2 is large. 1 over V to the 1 is large. So unless you get here all the terms up to V to the 6, you really need to go up to V to the 6 to get a sensible prediction to correlate with the data. Okay? So if you want this correlation to be precise to less than 1 radians, you are correlating two angles, two phases. There are two angles. So you want this correlation to be precise to less than 1 radians, you really need to go to higher order in this prediction of the phase of the waveform. What did I do? Oh. Okay. Okay, so you really need to go to this high order. We don't go in this course to V to the 6. I just show you the V to the... There is what? Ah, the undo button. Oh, thank you for future reference. Thank you. Yes. Yes. As you can see, I'm not digitally native. Native digital. How do you say? Okay. So, yes? Yes. Correlate. Yes. Why the noise? No, of course, the noise, okay, the noise is not due to gravitational wave. So gravitational wave has a specific pattern that, you know, the frequency increasing, the amplitude increasing. It might happen every now and then the noise may mimic a gravitational wave signal. So what we do is that we lay down hundreds of thousands of possible signals by varying all the astrophysical parameters. We take a correlation with one detector and we take the correlation in the other detector, and we see when there is a coincidence spike in the two detectors at the same time. And then we do the same thing when the two streams of the two detectors are shifted. So then if you find a correlation between shifted strain of detector, then that correlation is spurious. It's just due to noise, that's for sure. Not because you shift for 2 seconds, the gravitational wave going from one detector to the other takes milliseconds. As we demonstrated, it goes with the speed of light. We'll demonstrate that. Okay, so you have an idea of what is the spurious correlation by taking the shifted, and you take 1 million shifts and you take the average. So you know how many spurious correlation you can get. And then you take the correlation at 0 shift. Okay, not exactly 0 shift because you can allow some mismatch because the gravitational wave is traveling with the finite speed. So we'll hit one detector less, at some time and the other detector at some other time. But that's millisecond. That's not 1 second shift. So and then we see how many correlation we have at 0 shift and how many correlation we have with 1 second shift, 2 second shift, and 3 second shift. And we see 100 correlation at 0 shift and 50 correlation and on average some shift. Then we expect that 50 are real. Okay, that's the bottom line. Of course, you can quantify my reasoning way more than this, but this is the idea. But sure, there are spurious correlation. The detector has noise which is non-Gaussian. So, but the nice thing is that basically if you go to high enough signal-to-noise ratio, the spurious detection decays exponentially with the signal-to-noise ratio. Again, the signal-to-noise ratio we're going to define. But intuitively, you can understand what is signal-to-noise ratio. It's the ratio of the signal to the noise, as the definition says. Okay? So if you go to very high signal-to-noise ratio, you can expect that the number of spurious coincidences at high signal decays really exponentially. So you look how many spurious coincidences you have, you put a cutoff, you say, I want to have a spurious detection less than 1 per year, less than 1 per 10 years. I mean, that's up to you. And then from that signal to noise ratio on, whatever you get, you call it detection. Okay, this is very, I mean, things are more sophisticated than this, but this is the bottom line. I think for the level of this introductory course, this is enough. Okay, what more did I want to say at the introductory level before we go to the very interesting, slash boring stuff of doing the actual computation? I think, yes, that's it. This concludes my introductory part. So I kind of flash what are the astrophysical setup, where the signal come from, how do we kind of model it, how do we kind of measure it, and now all of this was hand waved, as I waving my hands, and from now on, no, we do things quantitatively, and we compute things. Okay, so this is a good time to stop for questions before we start the hard stuff. Okay, so you're ready for the hard stuff now. Good. So let's make, I can make a new page, no? To mark the change of continuity. Okay, so where do we start? Well, you know, this is I'm a theoretician as a education, then I became more phenomenologist, but now I'm a theoretician. So if you want to study gravitational wave, where would you start from? I mean, we start from the basics. We start from the Einstein equation. It's all in there. After all, gravitational wave is just all the phenomenology you can do by linearizing this equation on the top of Minkowski. So we take the metric to be, and then you say, oh no, but this is a cosmology school. I mean, how can you expand over Minkowski? Well, it turns out that the effect of cosmological expansion can be factorized very nicely and very simply. So in order not to bring all the difficulty at once and be submerged by all the difficulties, let's split the difficulties. Let's first expand over Minkowski, then we add the complication of the expansion of the universe. And by the way, all what I do here has to do with the background expansion of the universe. The universe is homogeneous and no fluctuation. Of course, there are a lot of nice things you can do with considering correlation, or that the galaxies are not homogeneously distributed, but maybe Matthias will talk about it next week. Anyway, I will not talk about it. So we do this, and though this is a major simplification because of course, this is a nonlinear theory. Gravity interacts with itself, interacts with anything. But when you simplify this and you go to linear level, then the equation becomes much simpler. So what do you have? The G mu is equal to -1/2. I mean, basically, this is a two tensor. There are all possible ways in which you can write the two indices over H mu. There are these four possible ways. I mean, this look like some ugly formula, but the more you look at it, the more you find it reasonable. So there must be a structure like this, d mu with the 2 alpha contracted, with 2 indices contracted mu, and there must be a structure like this. Okay, here I already wrote the coefficient because I knew it, but you don't. I mean, and then here there is a coefficient which is 1/2. I mean, the only non-trivial thing about this expansion are the pre-coefficient. This is -1/2, this is -1/2, and this is +1/2. All the rest is fixed by symmetry. No? You have H mu, you know that the Einstein tensor has two derivatives. This is linear level, so you cannot have H squared because by definition I took it out. So these are the only four structures, actually three structures, because this must be symmetric, so it must appear in this combination. There are only these three structures that can happen. The only non-trivial thing is that this structure is -1/2, this structure is -1/2, this structure is +1/2. All the rest is fixed. You cannot have this. Okay. What happens? Now, it happens that is kind of easier. Undo. Where is the undo? Desfacer. Desfacer. It happens that it's kind of easier to work in this other variable, but it's just h bar mu, which is h mu -1/2 eta mu h. Okay, you can work with this other variable, and then the equation looks a little bit more simpler. The equation looks like this. Yes, there is a box h mu, and then there is this bar plus eta mu d rho d sigma h bar rho sigma. Yes, by the way, there was this structure that I didn't wrote it earlier because it just didn't appear. It could have appeared, but it just doesn't. And then you have the structure minus d mu d rho h rho nu d nu d rho h rho mu. Okay, yes. You see, the structure is a bit sorry, I mean, this might sound a bit boring, but it's good that you familiarize it a bit. Okay, look at this. In this h bar variable, then I write, it's kind of similar. So it disappeared the trace. So there was the structure with the trace that disappeared, and it appeared this other structure that actually wasn't appearing here above. So look at this equation. These equations are linear. So you think, okay, linear equations are the best we can offer. I mean, we cannot make anything simpler than linear equations. But look at this, they're still coupled, no? Basically, all the temporalization couples to all the other temporalization. So it's still not very comfortable. And then there is another problem, that we know there is a coordinate transformation. Ah, sorry, this is just plus. I mean, the two must appear with the same coefficient. So here there is a coefficient which happens to be -1, but even if you don't remember the coefficient, you know that this structure must appear together with this, no? Because otherwise it wouldn't be symmetric. This object is G mu, no? That's it must be symmetric. So whenever you have this structure, you must have the two in one. They always go together. And the coefficient happens to be -1 just because, -1/2 actually. No, yeah, -1. There is a 1/2 in front of everything, but that's not important. What is important is that this structure can have heuristically any coefficient. It happens to be this. This structure in principle can have any coefficient. In principle can be this. This structure can have any coefficient, but it happens to be this. But these two structures might come together because of symmetry of the Einstein tensor. Okay, so this equation is not too difficult. I mean, if you put on a computer, it's linear. But the problem is that you see, if you want to solve for 0, 0, for instance, you must know all the polarization. If you want to solve for XX, you must know all the other polarization. But at the same time, we have the freedom for coordinate reparametrization, for the general relativistic. And so suppose, and again, we do a linearized transformation such that x prime is equal to x plus some xi mu, where xi is completely arbitrary. And so we can use this parametrization to see that the H is transformed goes to an H mini prime equal to the old H mini minus xi mi comma ni minus xi mi comma mi. Okay. I mean, you just expand this eta plus h, and here you expand this x become x prime minus xi, x become x prime minus xi. Of course, you can write everything I write here, but the notes contain everything. This is what I write on the board is a sample of the notes. And okay, so when we do this, you say, oh, okay, but let's use this, and let's impose then that the mu h bar mu nu is equal to 0. I mean, this is the same what you do in electromagnetics, no? You get, for the equation of electromagnetics, you would get box a mu plus d mu a nu equal to j mu. And then this is kind of offending piece. And then you say, oh, but I go to a gauge where the dA is equal to 0, and then I'm left with my good box equation, my good relative equation. So I apply this here, and so look at how nice. All these pieces involve some divergence. So all these pieces go away in this gauge, which I can always, apply because of the coordinate transformation, and then I'm left with my favorite equation. Okay, here but it's not, this only works in the Lorentz gauge. The Lorentz gauge means this. The H bar, the divergence of H bar is equal to 0. I can choose that gauge, no? Because I have my Coulomb transformation. And now this is very easy to solve. How do I solve it? Done, I solved it. You like my way of solving differential equation. I mean, this is only half, as I said, yes, this is only half a joke, no? That means that I put the H, I convolve, in Fourier space, this is a real product. In direct space, I have to convolve the source with the green function, okay? But there is a problem here, you see? If you bring back this here, say, oh, but wait. Wait, what have I found? What have I found? I found that I have here temporalization, it's a symmetric two tensor, this is temporalization. All the temporalization satisfies a wave equation. By the way, this is, when I open this box, this means minus dt square plus Laplacian square h bar mu nu. So this equation is a wave equation. That means that whatever happens on R, say for a spherical wave, must actually happen on t minus R. It's a wave equation. And it tells you another thing, that this wave propagates with the speed of light. Yes, it's written here. By the way, since I'm gravitational wave astronomer, I prefer to say that light propagates with the speed of gravitational wave, just to be inclusive. But okay, let's keep to the standard way of saying. And so we learn two things. This is a wave, and this is propagated with the speed of gravitational wave, which is happens to be the same as the speed of light by the theory. But I have the feeling that I have 10 radiative degrees of freedom, and this is wrong. There are not 10 radiative degrees of freedom. First, because there are 4 conditions that not all 10 are physical, and second, because out of the 6 remaining, only 2 are radiative and 4 are longitudinal. You remember, I kind of demonstrated yesterday. Yesterday I demonstrated how the demonstration goes for the electromagnetic field. I have 2 radiative, 1 longitudinal, 1 pure gauge. I didn't do the demonstration for the gravitational field because that would take 1 hour and a half. But it's in the notes. The notes refer to the original paper doing that. You find in many books, so you don't have to trust me, but just go and look it for yourself. The actual physical decomposition tells me that I have 4 gauge degrees of freedom, so they're not physical. 4 longitudinal, that are basically mediate Newtonian attraction in general relativistic generalization, and 2 radiative. So out of these 10, only 2 will be radiative at the end. We'll see. And now we are showing by hand this. Okay. So, okay, let's do the following. Let's show by hand, not with the general argument that I sketched yesterday, because I only did it for electromagnetic field, but you can do exactly the same argument, just more complicated, because you have more polarization for the gravitational field. Let's do it by hand and demonstrate that only 2 of these 10 degrees of freedom are radiative. So what happens here? I have an h mu nu. Okay, let's make a new page. New page. So what happens here is that I have an h mu nu, and so first I have an h mu nu, my h bar mu nu, and then you remember this can be changed by coordinate transformation. Goes into h mu prime, which is equal to h mu nu minus x mu nu minus x nu mu. Actually, the coordinate transformation for h bar is slightly different. There is here an h mu nu xi, but okay, this just follow trivially. And so what happens here is that what happens if I okay. So what happens if I already know the 4 conditions kill some 4 degrees of freedom. Now I want to kill more. And then in particular I want to restrict to this equation. Okay? Why I want to go to vacuum? Because you remember yesterday, again, the demonstration was not actually complete because I didn't do for gravity, but believe me, the demonstration I did for the electromagnetic field goes over the same for gravity. there were some fields that satisfied Poisson equation, and on the right hand side had a source term. And there was one equation, was the box that had the source term. So when you solve for the Poisson equation, basically the field has to follow the same behavior of the source. Whereas for the radiative field exists even in absence of the source. So when we put to 0 the source, we are sure we are killing all the longitudinal modes. The longitudinal modes, is the two charges that are attracting and repelling. They exist because they just follow the source. It's just a way to write in the field as giving the attraction and repulsion of the source. These fields, they exist also where the source is not there. So let's go to the vacuum case. And when we go to the vacuum case, we see that this equation is unaltered if we choose a coordinate transformation satisfying this. So we choose a specific coordinate transformation. We can do this, and we can apply this coordinate transformation when we are in the Lorentz gauge and still be in the Lorentz gauge. You see this? Because when we do this, the Lorentz gauge will be this. Okay? Sorry, this is the new one. Suppose we make a coordinate transformation with the coordinate shift c that satisfies the box equation. Then look at what happens here. This will become minus d mu c mu d nu minus box c nu and plus d nu d psi. So these two simplifies. And so you see, if we choose this specific a coordinate transformation with this specific, we can still make another coordinate transformation and still be in the Lorentz condition. Okay? So the coordinate transformation that we use to kill the divergence of h bar, we can still recycle it and make some additional coordinate transformation and still be in the Lorentz condition. And you see, once we do this, basically, means that box h bar min goes into this, where I define all of these as psi min. Okay? So, this is the transformation of h bar. It just inherited from the transformation of h. It transforms with this. We know that if we pick a new psi which has box psi equal to 0, then we don't go out of the Lorentz condition. So this equation holds, but then it means that this object, I have 4 more degrees of freedom to kill 4 more degrees of freedom that are inside this h bar. You remember this h bar were 10 initially, they became to 6 because of the Lorentz condition, but then on the top of the Lorentz condition, I can apply this further gauge transformation that keeps me inside the Lorentz condition, but I can kill 4 more degrees of freedom. You see, here I'm doing by hand what I kind of demonstrated yesterday. And demonstrating yesterday there are 4 degrees of freedom with our pure gauge, and those are killed by the Lorentz condition. There are 2 degrees of freedom that are radiative, but there are 4 degrees of freedom that are longitudinal. And these 4 degrees of freedom which are longitudinal, they die naturally in vacuum. And so in vacuum, I can kill them by a further gauge transformation that satisfies box C equal to 0. Since in vacuum box C is the same equation of box h bar, then I can reabsorb those 4 longitudinal degrees of freedom in vacuum and leave the only really truly radiative degrees of freedom. So in practice now it's almost trivial to do this. We just say that we use we use 3 Lorentz condition. For instance, 3 Lorentz condition we use to make this and there is use the form. Okay, let's use the Lorentz condition to make vanish these ones, H0I and H, the trace. Okay. Oops, sorry. We use 3 Lorentz conditions to make this vanish and that. Okay. This used to H vanish. Sorry. No, these are 4 conditions. Oops, sorry. That are set by XCB. Psi b is this extra coordinate transformation. These are 4 extra coordinate transformations that are always inside the Lorentz condition. Okay? And then I use this extra coordinate transformation to kill these 4 degrees of freedom. So in the H mu, I'm killing the trace, and I'm killing this. H0x, H0y, H0z, and I'm killing the trace. Then I do the following. The first of the Lorentz condition, I haven't yet used the Lorentz condition. I'm using this extra coordinate transformation that keeps me inside the Lorentz condition that I can only apply in vacuum. When I'm in vacuum, I can do this extra transformation that doesn't move me out of the Lorentz condition. And since box C is equal to 0, then, and since C min E is just shifting H min E, H bar, then I can do, this equal refers to the above equation. I can use the C min E to eat 4 more degrees of freedom. And so I can use this. This equation now becomes the EHI 0 plus the 0 H00 equal to 0. Okay, I killed 4 degrees of freedom with this extra coordinate transformation that I'm allowed to do only in vacuum, because only in vacuum that it can kill the H min E. So this was already 0 because of this. Now I'm using the Lorentz condition, and so I see that H00 is constant. But if H00 is constant, then it cannot be a wave. No? It's just an offset, so it doesn't belong to my radiative part. So I'm killing not only the trace, but I'm killing this piece. Then let's go on. The mu H mu I is equal to d0 H0I, that was already 0, plus dj Hji equal to 0. Okay, so you see I kill already 4 components by this extra coordinate. Then I'm using the first Lorentz condition, I kill 1 more. Then here I'm killing 3 more. Let's take, for instance, a plane wave which is propagating in the z direction. So the only derivative here will be to z. So zx, zy, and zz must be 0 because of this condition. Again, must be constant, strictly speaking. But again, a wave that is constant is not a wave, so it's 0. So at the end of the day, I'm left with only non-zero parameter, this one, and 1 in the diagonal because the trace has to be 0. So this is there. So at the end of the day, I'm killing 8 degrees of freedom, and that I'm leaving with 2 that really satisfies the Boss equation. These are 2 degrees of freedom. Okay, so I redemonstrated. I demonstrated in 2 ways. Yesterday, I demonstrated, again, only in the electromagnetic case, but it was a hint of what you do in the gravitational case, that there are some longitudinal degrees of freedom that are not waves, and 2 degrees of freedom that are waves. Today, I demonstrated by hand. I found that in vacuum, and only in vacuum, the longitudinal degrees of freedom can be killed by this extra coordinate transformation. I do this extra coordinate transformation, I kill whatever is not radiative, and then left, for instance, for a wave propagating in the z direction, I'm left with the H plus here, minus H plus here because the trace has to be 0, and H cross and H cross here. Sorry, it doesn't look like they're on the same line. Let's rewrite on the same line. Okay, and of course this is symmetric, so whenever there is a 0, there is a 0 also here. Okay, so this is the demonstration by hand. There are 2 radiative degrees of freedom, and then they are transverse. So the easy way to implement this in your computation is that you take the perturbations, H min E, you just kill all components which have a time entry. So you immediately go from h mini to hij. So whatever is h00, h0i, you kill it by hand because you have that freedom of extra freedom in vacuum of gauge transformation. And then if you want to project out the transverse direction, because of the Lorentz gauge condition, you project out the divergence, you do the following. You apply this projector, which is universally called lambda ijkl. Lambda ijkl is made of a product of two projectors. And this projector is delta ij minus ni nj. What this projector does, this is the projector that you would apply to the electromagnetic tensor to pick the transverse direction. You see, if you apply this to electromagnetic tensor, the longitudinal part is set to 0. The transverse part survives and they are equal to themselves. So this is the transverse projector for the electromagnetic tensor. Basically, for the gravitational case, you have to square it and you have to take out the trace. This is the projector that takes a generic space-space perturbation of the metric and project it into the two radiative components. Of course, this h must be at the beginning in the Lorentz gauge, but we never will be out of the Lorentz gauge. 5 minutes, yes, thanks. Okay, so you start with the Lorentz gauge, you apply this double projector, so this kills the transverse and this kills the trace altogether. And this is the projector that does it on the electromagnetic field, which has only one component. And now I can start, in 5 minutes I won't be able to finish, but I can start derivating the quadruple formula. How do we get to that v to the 10? Any questions so far? Okay, let's derivate the v to the 10 then. Yeah, I won't finish today. So at the end of the day, my HIG TT must be equal to, so there was a minus 1/2, so it was minus 1/2 HIG. Was the, I have to 1 over box. 1 over box means the green function. The green function is, transverse traceless. Transverse traceless. Okay, because I am applying the transversality because of the Lorentz condition, and then one of the conditions of this extra degrees of freedom that I can make kills the trace also. So at the end of the day, I'm killing all the space, all the time component, either time and time space, and out of the space component, I'm killing the trace, and I'm killing the longitudinal one, the one longitudinal to the direction of propagation. So you remember what is the I apply the retarded boundary condition. Okay, and then there is minus 1 over 4 pi because of the green function as normalized like this. Yes? Yes, just a second. So there is an 8 pi g here because it was in the Einstein equation, and there is a lambda ijkl, the projector. Okay, so this is the solution. When I take out the minus 1/2, okay, then I get the pi goes away, 4, I get plus 4 g lambda ijk. So very good. What is lambda ijkl? So lambda ijkl does, I don't have to bring it up, but I have to go to the previous page. Lambda ijkl does for me for free what I did it by hand. You remember, I started with the Lorentz gauge, and then on the top of the Lorentz gauge, I took out 4 more degrees of freedom. They were the longitudinal ones that dies in vacuum. And how did I did that? No, I introduced that further gauge transformation that satisfies box phi equal to 0 to kill those. And when I do those, I kill the time component, I kill the trace, and when I use the Lorentz condition, I kill the transverse. Okay? So lambda does all of this for me, for free. So take AI, a vector field, and then I apply a PAJ. I apply a PIJ over AI. My PIJ, if no, is my delta j minus n hat I n hat j. You remember what I did yesterday? This I decompose into longitudinal part into a transverse part. The transverse part is orthogonal to n, so when I contract with n, doesn't do anything. So I have just delta times the transverse part. The longitudinal part is parallel to n, so when I contract with n, it gives itself, then it gives me itself minus itself. So this projector sets to 0 the longitudinal part and leaves unaltered the transverse part. So lambda is just the square of it, because the gravitational tensor are two indices, so I have to project each of the two indices. And then I have to take out the trace. For this, there is the second piece. There is a p times p minus 1/2 pp to take out the trace. Okay, so the lambda I have to put it here to project out the the transverse and I mean to project in to keep the transfer place and to project out the longitudinal piece and to keep out the transfer place. I guess here I skipped that I use the green function, the retarded green function, but I guess everybody should know it, no? The green function is, yes? Sorry? Ah, and 3, sorry, so yeah, it was 3, of course. I'm integrating in 3 dimensions, yes. Yes, I mean, the green function, yes. Okay, so I integrated, I mean, nobody is scandalized by this green function, yes? Is anybody? Is anybody having any trouble with this green function? This is, I mean, you find in Jackson, is, yes. No. Sure, no, in the dimension, the counting of degrees of freedom changes, yes. I was just, we never go out of 3 plus 1 dimension, okay. No. But yes. And also the shape of the green function changes. I mean, of course, that doesn't go with 1 over r, it goes with 1 over r to the d minus 2. Okay, so this is the standard retarded green function. You put it there and you get the result. I guess I should wrap up, right? Yes. So what we'll see tomorrow, that will be the heart of our treatment of the gravitational wave sources, is, see, this is ugly, because we have the dependent on x prime, both in the here, which is the space dependent of x, but we have the dependent on x prime also in the time part of the source. Well, it has to be so, because this must be the retarded time, no? The field at time t cannot depend on the source of time t. Must depend on the source at retarded time. But look at this, and then I conclude. Let me give you qualitatively what is happening here. You know? My observer is here. So my observer is this big eye, and my source is somewhere far away in a far distant galaxy a long time away, a long time ago. Okay, and its size is very small. It's, I mean, we're not looking at the galaxy now. We are looking at a binary system, kilometer size, whereas this distance is hundreds of megaparsec, say, and this distance is hundreds of kilometers. Okay, so this is way smaller than that. And so what happens is that this point of the source, we don't see it exactly at the same time as this point of the source. No? This point of the source is closer to us, so we see at some time. This point of the source is farther from us, so we see at a slightly earlier time. But this distance is very small compared to r. So what do? We do a Taylor expansion of this dependent on x prime, so that we factorize the dependent on x prime inside here, and we keep the time dependence independent on x prime, just at the price of adding derivatives. It's a Taylor expansion. No? We just Taylor expand the dependence of x prime of this source, but then we have to derive over time. So we get some source at instant, all at the same time, plus source times x prime derivative, plus source with 2 derivative times x prime square, and so on. Okay, we are doing an expansion, and then I really finish. And then I let you ponder until tomorrow. What is the small, when you make a Taylor expansion, you must have in your mind what is the small parameter of the expansion. Okay, otherwise it doesn't make any sense. So we have energy momentum tensor with some component. We get t minus r x prime plus t dot t minus r x prime dot n, and so on, where t double dot at retarded time. Now the retarded time is the same for all points because I'm Taylor expanding, but then I'm weighting the derivative of the source by this power of the distance of the source to some reference point. So for this Taylor expansion to make sense, this has to be smaller than that, this has to be smaller than that, and so on. And then I let you think about what is the parameter, small parameter that allows you to go from here to there, and from there to there. So this is crucial in our understanding of gravitational wave production by a compact source. And the small parameter going from here to there is, sorry, the time is finished, I will tell you tomorrow. Okay. Yeah, but think about, I mean, if you leave the week and you understand only this thing, I would be happy for you. I mean, this is a very deep thing that you have to understand. But I will tell you tomorrow. But in the meantime, you might understand on your own from now to tomorrow.
Time for one or two questions. Okay. The lectures are the slides are going to be uploaded to the website.
Yes. No, but I have also my notes. Actually, my notes I can upload to my personal webpage. The problem yesterday, I don't know why I couldn't connect to my webpage in São Paulo. I will try again today. Actually, in my webpage there is a version of the notes from some older school, but I'm going to update with this material.
So we can go for lunch and we reconvene at 4.